Hello guys, welcome to lecture 10. In this lecture we are going to study implantable antennas for biomedical applications. Okay, in this lecture we will study some papers, different designs. Okay, and now people are working to reduce the size of the implantable antennas. Okay, now a lot of research has been done on 7 cross 7 millimeter scale, and now people are going to reduce the size up to 5 cross 5 millimeter scale. Okay, here we will discuss some papers. Okay, and in this paper I suggest you to study these papers. Okay, and what we can do here, the first one that I told you, you need to achieve circular polarization in your each design. Whatever you design, I suggest you to make your design circularly polarized. Okay, because this is one kind of novelty. Okay. The other thing, you need to achieve a compact size less than 5 cross 5 millimeter scale. Okay, or 7 cross 7 is also acceptable but there should be some novelties in the design, as I told you before. Okay, I will tell you which type of novelties we can get in this implantable antenna. Okay, the other thing, you need to achieve wide bandwidth. Okay, so that it covers or it can be comparable with the previous research, because in the previous research a lot of research has been done on single band antenna, or on a dual band or multi band antenna, but less work has been done on the wide band antenna. Okay, or it can be more wide band. Okay, so the other thing, it is implanted inside a human body and for biotelemetry applications. Okay. Okay, so you can see here, this is a very simple design, as I showed earlier. This is a CPW ground plane. Okay, and the patch, you can see this is a modified patch, and it is a circularly polarized, and the size of this antenna is very small. It has a length of 5 millimeter and the width is 3 millimeter. Okay, yeah, it means it is 5 cross 3 millimeters square area. 5 cross 3 millimeter square. Here one question arises, is this size inside the human tissue, or is this size inside in free space? Okay, actually in most of the papers, researchers design antennas in free, not in free space. Okay, they do not target free space. Okay, they only target inside a human body. In most of the design, what we do, first we design the antennas, and then we test on the human tissues and check whether the results are compatible or stable inside the human body or not. Okay, but in case of the implantable antennas, it is optional that you design the antenna in free space and then test inside the human body and check whether the results are stable or not. Okay, people do not focus in free space, I mean researchers. Okay, it can be inside human body, your human tissue. Okay, people do not focus this one. Okay, but in some of my papers I design antennas. If you get this one, like if you make the implantable antenna in free space and it is also working in human body, then this is also another kind of novelty. Okay, because in when you insert the antenna in human tissue, the results will surely be changed because of the high relative permittivity of the skin. Okay, and or the muscle. Okay, so but if you do not want to make the design in free space, because if you design the antenna in free space, the size of the antenna will be large. Okay, and also you need to check whether it is working inside human body or not. Okay, but if you only design the antenna in human body, then it will be less than 5 cross 5 or 7 cross 7. Okay, or maybe more less. Okay, so in this design, first I designed this antenna in free space. Okay, this is a monopole antenna. Okay, and you can see this is the result in free space. Okay, this is the S11 that has a wide bandwidth. Okay, you can see here. Okay, this is the bandwidth, and this is the axial ratio. Okay, in free space. But in the then I tested the antenna in different tissues of the human body. Like I tested it in free space. The red one is in free space. The second I tested in inside skin. Okay. The green one you can see it is also resonating at 5.8, and then inside fat, and you can see the blue one is inside fat and also inside muscle. Okay. You can see it is less than 10 dB. Okay, at 5.8 gigahertz. So this is also another kind of novelty if your antenna is working in multi tissues. Okay, because in most of the cases your antenna works only in one tissue, like maybe in skin or maybe in fat or maybe in muscle. We only check two kind of tissue. One is the skin, okay, and the other one is the muscle. Okay, forget the fat. Okay, because in practical use fat is not available, only skin. For the skin we use skin mimicking gel, the name of the gel that has the same properties as the human tissues. Okay, and for the muscle we use the pork material, pork pork. Okay, that has the same properties of the like a human body. Okay. Okay, so you can see here the behavior of the axial ratio. It is 3 less than 3 dB in all of the cases. Okay, inside fat, skin and muscle. Okay, and this antenna is working both in free space and inside human tissues. Okay, and you can see here the size. I have compared the results with the previous research. Okay, I have very small size than the previous research. Okay. Okay, I will tell you which paper you need to follow. This is just an idea to share with you that how can we design if you want to make a monopole antenna. But in the case of the implantable antenna, I suggest you to make a patch antenna. Okay, slotted patch antenna fed by a coaxial probe. Okay, okay, like this one. Okay. First let me discuss one more paper that is also in free works in, as I told you in the previous lecture. This is the design that operated at 2.45 gigahertz. It has a size of 21 cross 13 millimeter square. Okay, you see it has a very large size than other designs. Okay, because it is working in both in free space and inside skin tissue. Okay, you can see here it is operated at 2.45 gigahertz. Okay, and also this is a circularly polarized antenna, and this is a human tissues, skin, fat and muscle. Okay, and I tested the antenna inside a skin tissue. Okay, and also this is also working inside muscle. Okay, and this is the behavior of the S11. Okay, so in this way you can design if you want to design in both in free space or in human tissues. Okay, but I told you for the IEEE journals I suggest you to only focus on one thing, like if you want to you need to check your design first, either you want to design in inside skin tissue or inside muscle. Okay, also you need to check either fabrication facility or measurements facility available for the skin tissue or for the muscle tissue. Okay, in our lab both of the facilities are available. Okay, inside skin tissue and I mean inside skin and inside muscle. Okay, so this is the paper that I want you to follow. Okay, and also I will share with you some more IEEE journals. Okay, I have so many, more than 200 papers of this I mean on implantable antennas. Okay, of many researchers. Okay, to follow. Okay, so you can see here this is a very simple design. This is a X-shaped slotted patch antenna. Okay, it has a size of I think 5 cross 5 millimeter square. Okay, here values are written. L1 and W1. Yes, it has a size of 7 cross 7 millimeter square. Okay, 7 cross 7. So this design is this antenna is designed inside I think muscle or skin tissue. Okay, you need to simulate your design. You see, in the previous lecture we first designed the antenna and then we created the human tissues, but in the case of the implantable antenna you need to do reverse process. Okay, you need to design human tissue like skin first, and then you need to design antenna. Okay, so we will study in this case. Okay, this is very easy to design. Okay, like I'm going to design implantable antenna. I am going to design a new design. Okay, that maybe I will create a new shape. Okay, so I suggest you to keep the frequency band of 900 megahertz. Okay, because at 900 megahertz or 2.45 gigahertz. Okay, 2.45 gigahertz, and you need to only design inside human body, no need to design in free space. Okay, okay, so you can design in 900 megahertz or at 2.45 gigahertz. Okay, and you can use these size. Okay, just if you know the size, then you no need to do so many modification. Okay, you just need to play with the patch or with the ground. Okay, okay, now I'm going to design a new shape of the implantable antenna. Okay, this is a patch antenna, and here I write the frequency. It can, from 0.3 uh, to okay, or 3 can be, or you can use 0 to 3. Okay, because for the moment you don't know at which frequency your antenna will operate. Okay, so you can take multi frequencies here. Okay, so you need to test your antenna both inside skin or inside muscle. Okay, and then you need to check which muscle in which tissue it is showing best performance. Okay, so first, as I told you, in the implantable antenna you need to do the reverse process. You need to design the human tissue first, like skin. Okay, I am going to design skin tissue first. Skin, and I take the value of where how much we have used here. This is another paper in which you can take the size. You can take I think minus 50. Okay, by 2. Okay, and also you can take here 25. Okay, like this. Or you can take more if you want. It is not an issue. And here I'm creating a new material. Okay, of the skin tissue. Skin. Okay, and the conductivity I use here for the skin. They have tested inside muscle. Here I will, I think, return the values of the skin. Okay, anyway, I remember the values. For the epsilon, it is varies from 38 to 42. Okay, so you can take 38. Okay, or 40. 40, yes. And for the electrical conductivity you can take 0.88. Okay, Okay, so this is your skin tissue. Okay, this is your skin tissue. Okay, if you want you can hide this skin tissue. Okay, and this is your uh, WCS. Okay, now you can align WCS. Yes. Walaikum assalam.
I want to ask you, at this time, I think if we begin to design the antenna itself, I think we will use lambda G, yes, the guided wavelengths. It's better from the beginning, the design.
Lambda.
But what about the propagation speed? Is not a free space.
I did not understand what you are asking about.
Because now we decide the operating frequency, okay?
Yes, 915 megahertz.
It's okay, or 2.45.
Yes.
As you
Yes, for the moment we don't know at which frequency it will operate. Okay.
But at least I will use lambda G, yes, the guided complex if I need to use the equation from the beginning, okay?
Yes, actually, here in CST we write in millimeter, and then after once the design is ready, then you can calculate its value in lambda G.
But we don't need to care about the propagation speed of the EM electromagnetic inside this tissue.
No, I think no, it will not be any issue, because after this you will calculate all the other parameters that you need. Okay, like SCR values and many other things. Okay, first let us design this one and check at which frequency it operates, and then we calculate the other parameters.
Because as I said to you before, designing the antenna at this lower frequency, by default it will become a large size.
Yes, yes, according to the equation, yes, but here you need.
If you're using lambda G and we know the propagation speed.
Yes, actually, yes.
The propagation speed for the tissue, how we can get it?
Wait a minute. Let me write here. As I told you, for the lambda G, what was the formula? C over F resonance frequency, and here ER. Okay.
ER effective, I think.
Epsilon R. Okay, relative permittivity. Here you will write the speed of light. Okay, and like 8 cross whatever. Okay, and for the resonance frequency, if you want to design at 900 megahertz, then write here. Okay, and for the epsilon value, I think you will not write the value of the substrate. Okay, you will write the value of the skin tissue, because your antenna is now inside skin tissue that has a high relative permittivity. Okay, it has a high relative permittivity, and it will give you a very small size of the antenna.
Small size, sure.
Yes.
Thank you. So because I care about this is epsilon R, because this epsilon R not substrate itself.
Yes. Yes. That's why we will have a very large size.
Yes. Thank you.
Okay, now let's design the antenna, and this is your skin, and if you want you can hide this one. Okay, like click on right click on it, and you click on the hide. Okay, and it will hide. Okay, but in fact it is a skin, there is a skin tissue in this area. Okay, now click on the, let's create a substrate. Okay, the best substrate for the implantable antenna is Roger Ultralum, but it is not easily available, so I suggest you to use the Roger 5880 with 0. You can use.
Also, Sarosh, you said, of course, maybe the area itself of the skin is not a big matter, but the skin, I think you write here 25 millimeter, I think. 100 millimeter. Yes.
I write the area of the skin tissue is 50 cross 50 millimeter square.
Yes, it's not big matter, but I think the depth itself of the skin is not too much.
And it is not a big issue, okay, because suppose if you are taking 100 cross 100 millimeter square, and in practical use you also need to take a skin mimicking gel of size 100 cross 100 millimeter square, okay.
I talk about this issue because if I have a multi-layer like skin and fat or something, and as you see, as you show in your paper,
Yes,
if I want to put
yes,
antenna in this part and in this part and this part, I think
you can see I because only these tissues are available, like if you are only testing your antenna inside skin, forget
there
about
is no
the
standard.
fat and forget about the muscle, okay.
But there is no standard for the height of the skin. For example, you write here, I think 12, yeah.
Yeah, not I write I cross volume 50 cross 50 cross 50, okay.
Yes, about the height of the skin.
Yes, actually here you are testing the antenna inside a skin mimicking gel, okay, and you know the skin mimicking gel can be varied, but it has the same properties, okay. No need to worry about that. But if
Okay.
you want, we can take the size of the, we can be take 50, 25, okay, like this.
25. Yes.
Okay,
Thank you.
so you can see here this is your antenna, okay. But I hided this one, okay, and sorry, this is skin and I hided it. Now we are going to uh, design the antenna, okay, patch antenna. First substrate, okay, and then we are taking 5 cross uh, 5 millimeter scale, okay. Okay, you see the size is very small.
But it's better to start by antenna or by the environment around it. It is not big matter.
No, because your design is now inside skin, okay, and forget about the other things, okay.
No, I mean when implementing it in CCD starting.
Mm-hmm.
I know the calculation is different thing, but when I start designing CCD.
Yes, if you design the
Yes.
first antenna, like if you do not design the skin tissue, and you are going to design in free space, then your antenna will operate maybe at a high frequency, like at 28 or 38 gigahertz, okay. So because of the high
Yeah.
value of the relative permittivity of the skin tissue, it will not operate very high frequency, at very high frequency, okay. It will
No,
operate
I don't mean that. I mean about the drawing. When we start the drawing in CCT, just before any process or something, because we insert it.
yes, yes, it is already inside the skin tissue, okay.
Okay, thank you.
And for the I was telling that you can use Roger 5080 with these two thickness, okay. uh, 0.125, okay, millimeter, and 0.25 millimeter, okay. You can use these two thickness, okay, because in implantable antenna we need a very less thickness of the substrate, okay.
We need a very less volume, yeah.
Yes, it has a relative permittivity of 2.2, okay. Okay, I am using here TS or 5 and 0.125, okay. And the material Roger 5080. Wait a minute, I think I taken the value of, like, wait a minute, we set it. Okay, now click on it and none to all, okay. The size of the antenna is 2.5, not 5, okay. So we take 10, okay. Now it is 5 cross 5 millimeter square, okay. You see this is very small size of the antenna. uh, wait a minute, now it is okay. uh, it should be like this. Yes, dear Amrish, what you are saying, on what factor 5 by 2 is left, sir? I choose half value, 2.5 millimeter on the left side and 2.5 millimeter on the right side. Okay, and this is a symmetrical antenna. Okay, this is a square shape antenna, square shape substrate. Okay, you see the size is very small. We will create a patch. Okay, also I save this design, maybe it will give more better results. Okay, and it does not take much time in designing. Okay, okay, so we will simulate it multi times. Okay, to check the frequency. Okay, now let me change the size of color of the substrate. Okay, now it is visible. And first, as I told you, I suggest you to make many slots, and you can design any shape of both of the ground and the patch. Okay, to achieve circular polarization pattern. Okay, I also give you some of my designs in CST. Okay, first I'm going to create a outline. Okay, with this one. Okay, with this. Okay, so what we can design here. Okay, in let me what we can design. I am starting from the edge. Okay, I designed so many beautiful shapes in CST. I will show you in a while. Okay, you can write here 0.0175. Okay, the thickness of the patch 0.0175. Okay, so this is your patch. Okay, or even if you want, you can rotate this patch. Okay, make a copy and okay, in this way, because this is a benefit of the symmetrical size of the substrate. Okay, like this. Okay, and you can add this one. Okay, and write the name patch. Okay, so this is your patch. Okay, now you need to and in this small size of the antenna, you need to use shorting pins. Okay, to keep the size compact and to achieve lower frequency band. Okay, so you need to remember that if you want to, if you are going to design the ground plane, then you need to know where is your patch, so that you can connect the shorting pin. Okay, so you need to design ground according to the patch. Okay, like I'm going to first, let me align my WCS on the other side of the substrate. Okay, and then I click on the patch. Okay, now I create the outline. Okay, by watching at the this one. Okay, so from where I can start. Okay, uh, I can take small portion of the patch so that we can connect the shorting pin. Okay, and also a lot of research has been done, I told you, but what we will search in implantable antenna. I will give you more important ideas in the end of the lecture. Okay, Okay, so this is your small patch on the other side of the substrate. Okay, and you can make a copy of this one. Okay, you can see here this is a new shape, but you can connect this one with the shorting pin. Okay, if you want. Okay, so this is your patch. Okay, and you can see where is your patch. This is your patch. Okay, and where is your ground plane. Okay, first add all the ground planes. Okay, okay, now click on the patch. Okay, you can see you can easily connect the shorting pins. Okay, wherever you want, but you cannot connect at the center of the center of the patch. Okay, you cannot connect the shorting pin at the center of the patch. Okay, so you need to use the shorting pins on the edge side of the substrate. Okay, so I'm going to use a shorting pin here, or you can use on the ground pin. Okay, it is easy for you. You need to use a shorting pin of size 0.5 by 2, means 0.25 millimeter, or it can be less. Okay, you can use 0.2 millimeter of size. Okay, okay, this is your shorting pin. Okay, and the shorting pin must be connected with the uh, patch. Okay, ground and patch. Okay, so this is your shorting pin, and I'm taking minus TP. Minus TP means in the downward you have a thickness of this patch. Okay, and then you have a thickness of this substrate, so I'm writing here minus TS, the thickness of the substrate, and then you have a patch, so you write here minus TP. Okay, and click OK, and you can see it is connecting with the patch. Okay, this is your pin 1. Okay, you can use multi pins. Okay, and you can see you can change the color of the pin so that it is more visible. You can use red. Okay, this is your shorting pin. Okay, you can see this is your shorting pin that connects the ground and the patch. Okay, and you can even transform the pin like this. You can make a copy of the pin, but keep remember the ground and the patch. Okay, so you have two shorting pins, and now we want to feed the antenna. Okay, so in order to feed the antenna, you can use a very small patch. Okay, like this. You want to feed, okay, this antenna. Okay, and you need 0.1. Okay, this is okay, and you need to take minus TP. Okay, this one. Okay, and even you can transform this feed. This is your feed. Okay, that is inside the patch. Okay, you shift this one inside the ground plane. Okay, like this. Click copy, and okay. Now you have a patch, small patch, circular patch inside the patch and inside the ground plane. Now you need to add both. Okay, now it become one. Okay, and in order to feed, you need to go to the pick points, go to the pick circle center. Okay, click on the lower edge. Okay, and then again choose this one and select the other lower edge, okay, of the other patch. Now go to the simulation, use a discrete port, okay, and change inward direction, okay, and click OK. And you have a probe here. You can use coaxial probe here, okay, of 50 ohm. Okay, now we will simulate this design. Click save. Okay, we will simulate and check everything about it. Okay, so in the far field we need to check the 900 megahertz, 0.915. okay, we already save. Okay, normalize to fixed impedance and start simulation. In implantable antenna do not take much time in simulation. Okay, let's wait for the results and check at which frequency it is working.
Hello, Ahmed.
Yes.
I want to ask you, all implantable antenna simulate like that?
What? Which antenna?
All implantable antenna simulate like that?
Yes.
We don't make a waveguide port.
No, if I am using here discrete port if you want to feed the antenna with a coaxial probe. Okay, in these designs you can see here, here you can use waveguide port because here I am using a strip line. Okay, and in this case also I am using coaxial connector or a waveguide port here, but in this case, in this design, you can see here the shape of the antenna. You can see I use one shorting pin, okay, that connects the patch and the ground. Okay, and I use one this is a coaxial probe. Okay, and you feed in CST okay. You feed like this. Okay, as I have done. Okay, this is a simple way.
Because when you change the port like that port, you get small changing in frequency.
If you want you can create a coaxial probe here, but here in CST and also in practical you do not use a coaxial probe like a connector. Okay, because the connector is also very large in size than the antenna, so you need a mini connector. Okay, maybe here you can see.
Actually, actually, we designed ones for the capsule. I think they depending on the small battery.
Yes. Yes. Well, that one is the capsule endoscopy. You can see here like this.
Is maybe related to the small battery.
Yes.
I worked before in one paper in this one. Like capsule. Yes, a capsule, and also we use a discrete port. It was a folding capsule. We use a discrete port, and we designed the battery because I typically reject our paper and ask that to do it. It takes long time. Okay, that's great. Yes, yes.
Yes, this one you can see. This is a mini connector that we use for the implantable antennas, and this is your antenna. This one is your antenna, the very small size.
Okay. I think it's very difficult, not realistic to have a mini connector or something. Maybe using the battery or something.
Actually, where did you submit the paper? Because one of my friend paper was is accepted recently in IEEE transaction. He just designed a very simple antenna without any battery, without any capsule. Okay, he just designed the simple antenna and it has a multi-band and circularly polarized.
It was 6 months ago and they rejected. They said, okay, where's the battery? We need to design the battery. Alhamdulillah, we could finish it, but now we are writing.
Yes, maybe they ask about it. Maybe you have you have claimed in the title that you have designed a capsule-based implantable antenna.
Yes.
That's why.
We use a discrete. We use a discrete port.
Yes.
Yes. it's easy. Yeah.
Yes,
It's
implantable
formidable.
antenna are very easy just to achieve more wideband and to achieve circular polarization. If you achieve this one, then you can easily defend your design.
Okay. And when we can put the antenna in the capsule, is for medical or for what exactly?
Yes, it.
Actually, for stomach, we need it for stomach.
Ah, okay.
Okay.
Yes, you can see the figure here.
You can take it as a tablet. Yeah.
I will send you this paper too. You can see here like this one. They have a figure like this. You can see this is capsule implantable. They have embedded the implantable antenna inside this capsule, and you can, if you eat it is like this one works like this. Okay.
Yes.
Yes. I want to ask about the powers, about the capsulate. I think the battery is the supply the DC, so the antenna need to the AC to work it. So we must do inside more component to the capsulate if you use to battery. Because battery is the DC and the DC is the frequency is 0. How to calculate that? How to antenna work that? So we must to increase more component to if you use to want battery. I think that.
Yes, I think so, because in this case they have used many things. Okay, like lens they have used camera, they have used lens holder and batteries. Okay, and many. This is biocompatible shield. Okay, made of capsule. Okay, and this is your.
Yes. We must to use a component that converted to the DC to AC.
It is very, very small, yes.
Yes.
But sometimes we believe in the folding antenna and the patch and something like this.
Yes,
it
but
was big and small, yeah.
But its fabrication is not easy. Okay, that's why most of the people like to work only simple of patch antenna.
Fabrication is very difficult about this part.
Yes, that's why many people like to work on simple design. Okay.
Is imported like nano.
It's very small, yeah.
Okay.
This is big issue. The big issue is the stomach permittivity itself. It causes trouble for us. Actually, this one point the paper is rejected. Anyway.
Okay, it is working at 1.5 gigahertz. Okay, we need to shift it this one. Okay, so let's check the surface current where it is resonating.
I think we need to improve the matching, I think.
Okay, let's check it 915 megahertz. Okay, so yes, this portion, okay, if you vary this one, okay, vary this width and opposite side of this one, okay, like of the ground, where is ground, this one, okay, this side of the ground is working for the 0.915 megahertz. Okay, also you can increase or decrease the shorting pins. Okay, to check what will happen if we use only one shorting pin. Okay, let's check it first.
Also the feeding point is very big issue also.
Yes. Because of this small size antenna.
Yeah.
You just move your arrow on the A by M current meter, and you can move up and down. Okay, click up and down, and then you can increase or decrease. There are a lot of papers of my friends. They have recently published in IEEE transaction. Okay, let me show you their papers. Where is the papers? As I told you, implantable and IEEE transaction easily accept implantable antenna if you have even small novelty, okay, some novelty. This is not my friend. Yes, these are my friends, okay. They are also Pakistani, okay.
Yes, he folded, yeah.
Yes, this is, you can see, simple design, but they have used superstrate and the substrate, okay, of different thickness of the substrate, okay. I think
Actually, I want to explore this point also, Brother Sarush. The superstrate, and I think in our antenna, if you use it, I think performance will become good.
yes, with superstrate it will become more compatible. Yes, actually, you use superstrate where you want to put this antenna inside a capsule, okay. You can see here they are using capsule, okay, but if you see the paper, they do not use superstrate, okay.
It's a tissue, yeah, just a tissue.
Yes, some people like to and some people do not like, okay, but if you want, we can use here they are also using superstrate.
You can try it. The radiation pattern maybe change you.
Yes, yes.
And the performance also. But the superstrate material, it is available also in your lab?
Yes, I think yes.
If you can have a property, could you send us, please?
Yes, I will send you. I will ask, maybe in most of the cases they use the same material for the substrate, okay. Like if they are using the Roger ultralum substrate for the substrate, then they will also use the same material for the superstrate, but with the different thickness, okay.
I hope we can target this journal. Actually, we try the letter, antenna propagation letter.
Yes, I want most of the people do work on this implantable antenna, okay. This is a very good topic, and application can easily be, we can target a good journal on implantable antennas.
I hope I triple letter at least at the beginning, because you know the letter has small number of papers and can also be validated maybe in almost in 1 month.
Yes, I designed many antennas on implantable, okay, but I did not publish yet. I am working on them. You can see the results, and they have very good shape.
But Brother Sarush, you said to us, from where we can bring maybe a lot of shapes. You said maybe there is something about the graph or something like you mentioned that I think 2 days ago or 3 days ago.
I mean, if you are not getting idea of designing, then you go to the graphic designing website and you can design different shapes, okay.
And we can modify it.
Yes, and this is the design I made. It has a size of 5 cross 5 millimeter, and it is wideband antenna, okay.
Yeah.
You can see I am working on it, okay. And this is the front view and side view. I use two shorting pins, okay, and this is the probe, okay. And you can see the results are very good. This is wideband, you can see.
It's a wideband, yeah.
Yes, in most of the research paper they only you saw they are single or multi-band, okay, but not much wideband. Yeah, this is also multi-band, okay, but I have some ideas in my mind that we can target to
actually one thing about something actually what about if I use the QR for implantable antenna? Actually I worked in it 2 days ago. I start working in it. QR code.
Yes, it can be a good idea if you are able.
Let me finish and I'll show you.
Yes, I have some ideas in implantable, okay. What we can do new, okay. Some ideas. The first idea is that in most of the papers you have seen the multi-band or single band antenna, okay. What if we make a wideband or ultra wideband, okay, implantable antenna, okay, wideband or UWB. Yes, it can be a good idea. I mean, if we achieve this one, then surely we can target IEEE transaction, okay. The second idea is reconfigurable implantable antenna.
I think it will become very difficult with this, I think, for the fabrication, brother.
Yes, only we will not use much diodes. We only use one diode. One diode. I think in one
I'm
of
afraid
the.
I think the size of the diode become bigger than the antenna. I am afraid.
I made one reconfigurable antenna. But I did not fabricate it yet. I show you now. Okay, this is
What about the size of the component?
actually, let me. This is the design and this is design. You can see very beautiful design. This is the front view and this is the back view. You see,
Yeah.
the shape is very beautiful. And here I can use diode. Okay, I used, I think, diode. This is the diode results with the diode. Okay, when diode is, yes, when diode is on, then it behaves blue like this. Okay, and when diode is off, then it is like this. Okay, this is inside skin. Okay, and diodes without ground new or inside muscle. Inside muscle it is like this. Okay, when diode is on, but there is no big difference. But in the case of the skin, it is showing like this. Okay, so this is a reconfigurable, frequency reconfigurable implantable antenna. But I am asking to my professor either if he can purchase a diode, a very small side diode, or if he able to purchase, then we can target reconfigurable antenna.
Yes. Nice.
So the second idea is the reconfigurable. Okay, frequency reconfigurable. Okay. Okay, the third idea, metamaterial based implantable. Okay, we can make a wideband, ultra wideband, that we can achieve. We can, if we work, we can achieve this one. Okay, and we no need to use a capsule and other thing. We can define our design very easily. Okay, the fourth thing, if we make both wideband plus CP plus circular polarization. Okay, this this design I was able to achieve wide bandwidth, and I think it is also wide circularly polarized, I think so. I am working on it to improve the circular polarization. Yes, you can see here
Yes, yes.
it also have yes.
Yes. It's interesting demand, yeah.
Yes, I am working on it, and in this way you can create a new shape. Okay, this is a very simple shape, just to know you, let you know. But for you can use different shapes. Okay, whatever you have in your mind. And if you once you make, you can see this is also a good shape. And
Yes.
also I show you one more papers that have very good shapes. You just need a good shape and good results.
Okay, to think is a shape itself, it take a time.
Yes, but once you decide, you see this is a very good design. Okay, and this is a novelty. They have used a very small patch array. Okay, on the
Yes.
ground plane.
And it's not difficult shape.
Yes, novel shapes are not difficult.
Yeah.
And see, they do not, they did not use a
You
capsule.
know, for the graphical, you said to us, listen to us. After that, we can invent from this another shape.
What?
If you possible, could you send us the graphical website so that we can also modify it?
Okay, yes, I will share with you. You see, they did not use capsule. They just simply fabricate the design and test it inside tissue.
Yes. Anyway, how we can use our phantom? I think you show us a paper. I think maybe mostly maybe 15 minutes ago. You use the same phantom and you inject the antenna inside it. We can use it. I see.
Which phantom you are talking about?
That for yesterday, I think. I think one paper you showed to us. Yes, this one. It's similar to. Yes, this one.
Yes.
I think he used the same. He used the same phantom.
Yes, I use the same. They have designed in HFSS software, that's why they have mentioned about the radiation box and other things. Okay.
So this phantom tissue, I can also insert the antenna inside it, yeah?
Yes, yes.
Become realistic, I think.
This antenna is operating at 1.5 gigahertz, and also this is showing circular polarization. So when we start working on the design, then I will help you and I will give you some ideas, and I will give you ideas about the shape, but how should be the shape, and then we will work together to target good journals. Okay.
Please.
Okay, I will show you current bar. How can you move your current bar?
Excuse me, sir. Sir, you have shown here your gain is around, I think, near 4 or 5 dBi. So I want to know what is the best range usually for the gain in gain and directivity. What is the best it considered? What is the range actually it's considered to be the best one and maximum limit?
Okay, let me describe here. There are three types of in CST you will find directivity. Okay, you no need or never need to check this one. Okay, directivity, forget this one. Okay, nobody ask about it. You need to check the realized gain, okay, or IEEE gain. Okay, we mostly use realized gain. We also call it peak gain. Okay. Okay, the gain of the antenna must be there is no limit. Okay, but it must be positive. Okay, like you have a 0 here and you have negative values here. Okay, and you have a positive values here. Okay, in case of the implantable antennas you have a negative gain. Okay, but in the case of the simple patch antenna or in free space antennas you have a positive gain. Okay, so it must be it's up to you how much you can achieve, but as if you achieve more and more, it means it is more good. Okay, for you and also for the research. People are working on it to increase the gain more and more. Okay, because in you can there are a lot of techniques like antenna arrays, or why antenna array is designed. It is just designed to make the pattern directional and to achieve the more gain, more than 10 dB, more than 20 dB. Okay, but in with a single element or single patch antenna you cannot achieve more than 10 dB. Okay, but you can if you achieve more like more than 1 or more than 2 or more than 5. Okay, it is much better if you achieve more gain. Okay, there is no limit. Okay, for the surface current I want to show you this one. You are asking about how the you can see here. If you click on this here on the top right corner, you can move your bar. Okay, like this. Okay, you can see this design is working at 1.5, and also it is showing a circular polarization. I think let me check X-ray ratio, and you can see it is below 3 dB. Okay, and also check on the other frequencies. Okay, only at 1.5 gigahertz it is showing a circular polarize. Okay, but it is very not wide, it is very less bandwidth. Okay, okay, in this way you can design implantable antennas. Okay, if you want to change the properties. Okay, you can, if you want, like you have used skin, if you want to test this antenna inside muscle. Okay, I'm writing here muscle. Okay, Okay, and then go to the materials. Okay, find the skin, right, double click on it. Okay, and you can change the relative permittivity of muscle. Okay, for the muscle it is 0 point I think 98. Yes, also you can change the name here, muscle. Okay, now you can see you have created a muscle. Okay, you have a kind of, yes,
if you insert antenna between two layers, I think will have different performance basically.
yes, surely we will have different performance, but in implantable antenna you only talk about one muscle or tissue. Okay, as I told you in this case, yes, that's why.
But what is the acceptable gain? Because our friend asked about what is the acceptable gain in case of implantable antenna.
Yes, let me share here. Okay, actually when you insert your implantable antenna inside the skin tissue or any human tissue, your antenna gain becomes more than minus 30, or it approaches to minus values. Okay, so in implantable antenna you need to move towards the positive side. Okay, like maybe you achieve more minus 10 dB, then it is acceptable. Okay, maybe it is minus 5 dB, it is acceptable. You need to go to the positive side. Okay, that is the main idea. Okay, because in the previous research, if you see the comparison table, maybe you will have in this paper. No,
I show you show minus 1 point something.
yes, let me show the comparison table here, and you can see.
It was minus 1 point something, I remember.
Okay, now you can see this is the gain. Okay, and you can see in the previous research it is minus 30 dB, 35 dB, minus 19.9 dB. Okay, so you need to achieve you can see they have achieved more good gain than the previous one. Okay, so you need to go towards the positive side. Okay, maybe
I think in your paper, I think you show us one paper, it was minus something. It was a small table for comparison. I don't remember which paper.
yes, this one you are talking about, this one or other one.
This one, minus 1.25, I think.
Yes, minus 1.25, but this is at 5.8 gigahertz, and the size is very small, and also I use many tissue layers here. You can see skin, fat and muscle. Okay, so for the we can also simulate this one inside muscle. Okay, but you know, but you now you understood the process to design implantable antenna. Okay, now you can is you just the main thing is to design a new shape with the new results. Okay, the shape must be good looking. Okay, that whenever when everybody see it says wow, it is a very nice
the problem is shape itself is a problem.
Yes.
You need to set a simple shape for the optimization become easy. Because if you make a complicated shape, has maybe circle or maybe triangle or something, you need to optimize all these items, and sometimes you found your shape become distorted.
Yes, but you know, if the even but IEEE general accept difficult complex shapes, not easy shapes.
Complex shape actually the optimization take long time.
Yes, but you will have more results. Okay, like you optimize the slot of many, like this one you can see the design is very good, but you need to optimize. But you see this portion, this left portion, right, down, and this one are all are same, the same length, so you no need to optimize all these, so you need to only one element. Okay,
this is the key. Yes.
this is the like array. You can see there are 4 elements array, and I am working on it. I have fabricated this one. I am working on this design.
Yeah.
And also this one, this is also a very good design.
Yeah.
At the end of the once we complete all the lectures, then we will, when we start our designing, then I will surely help you in every case. Okay, in I will guide you in every way, inshallah, because our main target is to target a good journal, and we will surely write. Okay.
Hope the door of the IEEE. This is our
Yes, I like it only IEEE, but
yeah.
now I have published a lot, but now I want to move towards IEEE transaction.
Inshallah.
Excuse me, Mr. Sarosh. How about the durations to publish from submission until to publish?
Can you repeat, please?
How much the time take from the submission to publish in IEEE?
Yes, if you going to target IEEE access, then it may takes in my both of the it depends on your paper. If your paper is very well written, then it takes 1 month. Okay, IEEE access take 1 month. Okay, every journal take at least 1 to 2 months. Okay, IEEE access take 1 month, IEEE transaction take 1.5 months. Okay, and also IEEE AWPL take around 1 month. Okay, but that depends. It depends either they accept your paper or they reject your paper. Okay, suppose if you submit your paper in IEEE access, in the first submission, in the first reviews, revision, they do not accept your paper, they will reject immediately, and they will give you so many comments, okay, to address them. And if your paper is well written, they will ask you to resubmit the paper, okay, after correcting, addressing the comments. Okay, and then after addressing the comments, you will resubmit your paper, and if they like your comments, and they will accept. If they do not like, maybe they will reject and do not ask you to resubmit, or maybe they will again reject your paper, and again ask you to address more comments and resubmit. Okay, but in my case, in the first revision, it was rejected, but in the second revision, I mean, when they give me the reviews and I submit, and they accept immediately.
Actually, 3 times for me. It is 3 times.
Yes.
This is the last one. But no, the problem you said to me about the region itself. They think, okay, we are in the Middle East, okay, they send to another kind of people, maybe they make everything difficult.
Okay, I give you some tips to target IEEE. Like first, you must have some senior member of IEEE in your journal. If you want some it may help you to give acceptance. Okay, senior member of
I am
IEEE.
senior. I am senior. Sarush. I have 2 years. I am senior member. They reject me.
Yes, but
Mr. Sarosh, can we, when the submission my paper, or maybe in the futures, could you share your name with my paper, or in the futures, because we work with you?
uh, what can you repeat? I did not understand what you mean.
In the future, when submission the paper, your name is right in the paper. So there's
Yes. Once you publish, it for future it will be the same.
Yes. So is like sharing for the submission, and also take the guidance from you. And sometimes maybe need actually the Arabic people, we need sometimes the proofwriting or proofreading that.
Yes, no worry. No worry, our target, if you are more motivated, then surely we will go towards IEEE journals, okay, and IEEE access and IEEE other journals. Okay, don't worry. If you are motivated, then I will surely help you.
Thank you very much. Thank you very much.
No worry. And also, as I told you, there is some also you notice most of the papers of Chinese and of other, like non-Muslims, I mean, they accept very easily paper. Okay, but if you are a Muslim, then they reject. Why? What is the reason? Because all the editors and the reviewers are Indian.
Yes, that's
kind of discrimination. It's a lobby. Yeah.
Yes, that's why. That's why I changed.
It's happened with me. IET transaction of antenna and propagation in 2017. I submit a paper in January, and I was waiting till June, and they reject us.
Yes.
After 1 month. After us, I because they said, okay, you need to do some measurement, something like that. But I have a lot of theory and equation. And after that, after 1 month, I saw a paper from Indian person. It is 4 page only, and it is accepted in 1 month. What? It's
Yes.
something very strange, actually.
I submitted my one paper, this paper, about 7 months ago, and now I got the reviews of this paper. Okay, this is a flexible circularly polarized implantable antenna, and I submitted it in a scientific report journal. Okay, and I hope.
It's good. It's good journal, but it is the charge is very high, very high.
Yes, and I got the reviews. You can see. Let me show you the reviews.
I think the work is good. Actually, it's good. It's good. For me, I tried with him 3 times. It's very good, actually.
Yes, I got these reviews.
It's reasonable. Review is reasonable. Totally reasonable.
Yes, here they ask question. The proposed monopole structure is the commonly used method to achieve wide CP bandwidth. What is the advantage of this design and why it is new for biomedical application? So you need to give more explanation of your to defend, and also if some reviewer ask you to cite the papers, so it means they are going to accept your paper. Okay, and if without acceptance, how we can cite their paper? That's why.
Yes, I know that happened with me before.
Yes.
A person he asked me to remove five reference and added another reference.
Yes, if you do not cite, they will reject. If you cite, they will accept.
Yes, he want to increase his citation.
Yes, and also we will discuss in the last lectures how to address comments, because I had so many students, and they even don't know how to address them, and I have to do it myself.
Yeah. Subhanallah, Subhanallah. But actually, Elsevier journal, like the AUE
Yes.
journal, it is good journal, but take long time, 6 months to have a
No,
publication.
no. If you are submitting in a free, if you submit in free journal, because AEU is a hybrid journal. Okay, if you submit in a paid, then it may take maybe 2 weeks or maybe 1 month. Okay.
For free, not open access.
What?
For free, not open access selection.
I mean open access.
Yeah, open access, yes. Open access, it will become fast, but for free, it takes 6 months.
Yes. Because in my paper I got reviews after 1.5 months. Okay. I also want to if someone like to target, because we have some good journals. Okay, I will suggest you which journals we should target. Okay, because I prefer you not to go towards the MDPI journal. Okay, for first one, I already have so many paper in MDPI, more than 12 journals in MDPI, but I do not want to focus MDPI, because MDPI is going down day by day, because some of my friends were rejected for the PhD or for the postdoctorate because of many journals in MDPI. Okay, so that's why I do not like to prefer now MDPI journal.
Sure.
So we have very good journals like AEU journal. Okay.
AEU journal, yeah.
Yes, AEU journal. Okay. There are some other journals like this scientific report. I do not prefer you to submit the paper here. Okay, because I have very bad experience with this one. Okay, because after 6 months they told me, sorry, we are not able to find the reviewers for your paper, so can you suggest as your reviewers? And I again send you the list of the reviewers, and then again after 3 months, after 2 months they give response. So, and also if you submit your paper here, they will copyright your paper. Okay, so that you are not able to submit in any other journal. Okay.
Yeah, sure.
So that's why I do not prefer a scientific report journal. Okay, so this is also a very good journal. It is a Q2 journal, and it has an impact factor of 3.77. Okay. And the second we will target, I can target IEEE access. Okay.
I had a bad experience with it.
Don't worry. I have submitted my 2 papers here.
No, my friend said to me, after the third time you don't need to submit to them. Every time they send to another different reviewer, and he asked totally different questions. Something totally strange.
Yes, I submitted my two papers here and both are accepted. And but if you take much time in addressing the comments, then maybe the reviewer may not be interested more. Okay, so you need to, once you receive the comments, you need to address them as soon as possible and submit them. Okay.
One week, brother Sarosh. 1 week. 1 week is not too much.
Yes, I don't know why. Maybe because of the
Oh,
region I told you before.
I don't know. These are very strange, actually.
We can target IEEE TEP, okay, transaction of antennas and propagation, or AWPL, okay, antennas and wireless propagation letter. These are very best journals, okay.
Or letter of it also is very easy, I think.
Yes, this one letter.
AWS.
Yes, and EU journal, IEEE SAS journal, IEEE TEP. I also do not recommend CMC journal, okay, Tech Science Press, because I also have very bad experience. Even my this paper was accepted 3 months ago, okay, but even I asked them to send me the invoice and other things. They, even journal editor, do not give you any kind of response. I'm fed up with this journal, okay. That's why I decided, no, never I will submit any paper here.
Actually, it is a Q3, I think, or Q4, something like this.
No, it is a Q. I think it is Q1. Now I think it is Q2. But first it was the uh, Q1 journal. Okay.
Actually, my friend sent to them actually a paper, and it was not good paper. Actually, they accepted in 1 month.
Yes.
I feel sad.
Yes, its
I feel
acceptance rate is very high. Its acceptance rate is
yes,
very high.
I felt very sad actually.
This paper only is strict with the template. Okay, if you do not follow the template, they will reject immediately.
What about the IEEE transaction on biomedical?
Yes.
I think in biomedical engineering is very good journal.
Yes, all IEEE journals are good journals. Okay, it depends on the quality of our paper. If we write a very good quality paper, then we can target these journals. Okay.
Also, severe engineering and technology. Also, maybe 2 or 3 years become Q1. And high impact factor, mostly 4 point something. It is very good journal.
Yes, also there is RF CAD journal. We can try also this one. This is Q2 journal, and but its acceptance rate is very low. Okay, but we can, yes, RF CAD, International Journal of Radio Frequency Computer Aided Engineering. Okay.
Oh, computer. This is I think this is for Wiley, yes.
Yes, for Wiley.
Okay, send me your paper. I am a reviewer there.
My friends are also a reviewer there.
I am a reviewer there.
Okay, I am also a reviewer of many journals. Okay, of elsewhere journal. Okay, and close. Or do you know close on journal? This is, yes, this is another Q1 journal, multidisciplinary journal. Okay, let me check here.
Actually, I don't prefer the multidisciplinary because I try to go to the special because.
Yes, I know. I mean, I just talking about this.
Yes, and also citation become good from the special journal.
Yes. And you know it has a high H index, more than 80 places. And this is Q1 journal. This is Q1 journal. But I never publish in close zone, but I am a reviewer of that journal. Okay, and also of MDPI and CMC and Mortal, I think. Okay, so our main target is to IEEE. There is another journal that is Q3, but it is purely on antennas.
It's better not to go to Q3 and Q4 because maybe in 1 year or something everything is changed. They may become out.
Yes.
It's better Q1, Q4.
Yes, I mean. Yes, I know. I mean, for those who are new, and surely they will not be able to target a high quality journals. So we have to target low Q3 or Q4 journal. This is in Dave journal, International Journal of Antennas and Propagation. This is a famous journal.
Yes, very famous journal. But I think it is Q2, I think also.
It is Q3.
Really?
Yes. We can check here.
No, you don't need to check it from SGR, brother Saroshi. It's better from Calirivate.
Yes, we can check Calirivate, but it is Q3 from.
SGR is Scopus because the Scopus scale is different from the Calirivate. Web of Science.
Yes, yes.
Totally different.
Anyway, this is but now maybe it goes up, maybe it is Q2 now. So we have these papers.
Do you know any journal belong to Web of Science?
All this Web of Science.
All these papers.
Yes. If they become Web of Science, surely 100% they are indexed in schools.
But sometimes no.
No. But no.
But sometimes I did.
Okay. We can talk later, okay? Because now time is going up and many people are waiting for the other. Okay. Yesterday I realized that most of the people got confused about the co-polarization and the cross polarization. I made 3 slides for you, okay, so that you understand the concept of the cross polarization and co-polarization. Okay, so both are almost the same, but the difference only this word. Okay, the same and the difference. Okay. You can see here, whenever you find radiation pattern like this that seems to be very small in size, so it means they are cross polarization. Okay, but here we will discuss in detail. Okay, the first one is the yes.
Resolution. Excuse me for disturbing you, but it's better to show it also by the by the axis of the antenna, because it's different. It's related to the axis of the design axis of the antenna, X, Y, Z.
Yes, I in this next slide I will explain. Okay, but for now we will study about the definition.
For phi and theta or something like this.
Yes, in the next slide we have. Okay. Yes, first one, we are just studying the definition. The first, co-polarization, it means when the polarization of both of the transmitting and the receiving antenna are the same. Okay, but in the case of the cross polarization, it is different. Okay, you can see, as I told you, if you find the radiation pattern less than -20 dB, okay, then it is for the cross polarization, and if you see a big one, then it is for the co-polarization. Okay, now let's discuss in brief detail. I take screenshot from this CST and I write here. Okay, you can see this is the main concept of the co-polarization and cross polarization. Okay, the first one is, if you talk about the first, in CST you will find option far field like this. Let me check, like this. Okay, in CST you want to find the this one. Okay, let me create a new folder to paste the data and explain in more detail. Okay, I am creating a new folder. Okay, I am writing here co and cross. Okay, I will paste graphs here. Okay, co and cross. Okay, polarization. Okay, first one, we have a far field. Go to the 2D plot. Yes, this is 2D plot, and you need to remove this pattern lines. Okay, now this is your far field. Okay, you see in the slides you have this one. Okay, and for the co-polarization, what you need to do, you need to go to the theta. Okay, yes, for E field. Okay, you have two options, theta and phi. Okay, but in this simple case, if you click on the far field, you will find ABS here. Okay, you don't need ABS here, you need a theta. Like if you click on the theta, you will find this one. Okay, theta. And then what you need to do, you can see here, for the theta, if you click on the theta, you can calculate the E field of the co-polarization and the cross polarization. Okay, and if you write the 90, then it is the co-polarization. Okay, but if you write the is 0, okay, it is your cross polarization. Okay, like if I click on the theta and I write here 90, then it is my cross co-polarization. Okay, so I write, I copy the data, I copy it and paste here. Okay, I paste it here and I write here, this is co-polarization, but in the case of the theta is equal, phi is equal to 90. Okay, phi is equal to 90 or whatever it can be. I already saved in the next slide. Okay, like this I will explain. Okay, in the E field, you can see, if you click on the theta, you will find the E field. If you click on the phi, you will find the H field for the both co-polarization and the cross polarization. Okay, so for the co-polarization, if you put the value is equal to 90, degree, then you will find the E field of the co-polarization. But if you write the value in 0 degree, then you will find the E field of the cross polarization. Okay, and in the case of the, then you need to go to the first you need to go to the theta, and you can change the 90 means co-polarization, and if you write here 0, then it will become a cross polarization. Okay, and in the same case, if you go to the phi, if you write that 0 here, it means it is a co-polarization. Okay, and if you write 90 here, it means it is a cross polarization. Okay, like this. You see, here it is 90. Okay, but in the case of the phi, it is 0. Okay, this is co-polarization. Okay, I will share these slides, okay, with you. Okay, also I will take snap, or I will send you by email. Okay, so that you understand the concept of the co-polarization and cross polarization. Okay, and in the cross polarization, here you have a theta, and you will put, if you put the 0 degree, then it is give you cross polarization. Okay, and if you have a phi, if you put 90 degree, then it will give you cross polarization. Okay, in simple words, theta is equal to 90, phi is equal to 0, give you co-polarization, and theta is equal to 0, phi is equal to 90, give you cross polarization. Okay, and after pasting the graphs in one folder, then you will find like this. Okay, like this. You see, you have a co-polarization, and blue and green are the co-polarization. Okay, the other one are the cross polarization, and you see the results are good, because it is less than minus 40 up to minus 35 dB. Okay, it should be less than minus 20 or minus 25 dB. Okay, so in this way you can easily plot your co-polarization and cross polarization. Okay, and also once you pasted the data in one folder, you can click on it and go to the post processing and can import the data easily. Okay, so I will share these slides with you. Okay, I hope in this way you will more understand, okay, about co-polarization and cross polarization.
Thank you, Brother Sarosh. But it also is depend on the your design axis, Brother Sarosh. If you design the antenna in XY, because some people in some papers they may design maybe in YZ.
Yes, because if I tell about the XY axis, then people may again confuse. Okay, but they must know about the phi is equal to 90. You will have a XY plane. Where is the, because in the previous lecture I described that if phi is equal to 90, we have a XY plane. Okay, XY plane, Y plane. Okay, but in the case of the this is in the case of the co-polarization. Okay, but in the case of the cross polarization, it is become your YZ plane. Okay, phi is equal to 90. Okay, if I tell this, people again confuse about it, because even they did not study the paper and they don't know.
Because you know the researcher in the paper sometimes you know they design in different plane. If you read the paper,
yes, I know. That's why.
Yeah.
But
it happened with me maybe 10 years ago when I was confusing, but I get used.
But just keep this in your mind. Okay, what we have for the E
I
field.
think it's something I found a wrong in one paper in pairs. I think one year ago in my antenna. They made totally wrong, but it accepted. I don't know why. Maybe the reviewer does not concentrate about this point.
Maybe because in every journal, yes, in most of the journals, reviewers are of different fields. Okay, so maybe they don't have enough knowledge about that.
But it was totally wrong.
Yeah.
The author. I don't know.
Okay, let's check the results inside muscle.
Mr. Sarash,
Yes.
in the case of implantable antennas,
Mm-hmm.
can we measure EMI and EMC to know the interference between other devices?
What do you mean?
Because it's very important, especially in the medical.
You mean this one?
I mean electromagnetic interference and compatibility.
For the compatibility, for you can calculate the SAR values. Okay, actually in this case of the SAR value, the concept is different as in the human body antennas. Okay, as I told you in the previous lectures, the human body antennas have SAR values less than 1.6 for 1 gram and less than 2 watt per kg for 10 gram. But in the case of the implantable antenna, you will not get these type of values.
Like
Like
for EMI, for the interference.
for the interference, I even did not understand your concept. What do you mean interference? Because there is a
I
link
mean,
budget.
there
Okay.
were interference between the other device.
In that case, you calculate this one. Okay, link budget analysis. You know link budget analysis.
Maybe other device effect on this antenna.
Actually, link budget analysis, like you have a let me draw here. Like you have an antenna. Okay, the proposed antenna you designed. Okay, and you have a very small patch antenna. Okay, and you calculate the distance. You mean you are embedded your antenna, implanted your antenna inside a human body, and there is another antenna outside in free space, and they are sending information from one device to another. Okay, and how much distance they are covering. Okay, and in this way, in order to calculate the distance and other thing, you calculate the link budget analysis. Okay, to calculate the distance at how much distance, like how much distance you can collect the information of to this antenna. Okay, so in that case you calculate the link budget analysis. Okay, so there are formulas you need to write the MATLAB code or like this. Okay, and sometimes in HFSS you directly calculate the link budget analysis, but in the case of the CST, I am not sure about, because I send my designs, import my design in HFSS, and I calculate in HFSS, or send my to my friends to calculate this one. Okay,
so we cannot study or measure EMI.
In most of the papers I did not see they have measured or not. Okay, but
Also, almost. I mean, I read many papers. They put these values of EMI, especially for medical antennas.
Yes, that one is for the imaging applications. Okay, imaging or other application,
yes,
but
especially imaging.
yes, but here we are talking about implantable antennas, that's why.
Okay.
Sarush, could you send us these reference papers which you showed today?
I have a folder of the papers. I will create a zip file and then I will share with you. Okay,
It is the same which you already, I think, showed to us, yeah?
yeah, let me show you this one. I mean talking about this one, I have a folder, this one. Okay, these are all IEEE transaction papers. Okay,
Could you also your paper in this, I think, this field, yeah?
yes, I will send you.
Okay, so your paper is also here? Your papers?
Not here. This is in Hindawi journal. Okay, you can write the title of the paper. Okay, and you can easily download.
Yes, I think it's very.
And another paper got accepted, and I hope it will publish maybe today or tomorrow. Okay, the other paper is this one. The design is very good, and this is a beer shaped antenna. This is the paper. Where is the final version? Wait a minute. Where is the final version? Okay, I think I submitted in this way, but this is another paper accepted on implantable antennas. Okay,
No problem, we can wait till it published.
yes, you can.
because sometimes sometimes changing something, I think, and editing something.
Yes, this is a beer shaped implantable antenna, and shape is very nice, and I use one shorting pin at this side. Okay, this is not a finalized version, I mean the that is published. Okay, because there is a shorting pin in this side and I did not add the shorting pin here. Okay, so this is the design. And
also, I will hope Sarosh for the session for publication of the publication and to show how we make this layer separately. You said you do it in I think
this is
I
done
think
in PowerPoint.
Yes, we hope to show us it, please.
Yes, on the
somebody said I think there is an option in HFSS you can do it other than transfer.
In HFSS, I think yes, there is option to make your layer transparent. Okay.
But he didn't show to me actually.
But these figures are designed in PowerPoint. Okay. Also this one and other one. Okay. In PowerPoint, I think when you create a I did this for a long time ago, but let me check here. You create like this. Okay, just rotate it like this. Okay, and double click on it and you will find option shape effects. Okay, and in the 3D rotation maybe you will find options like this. Okay, and go to the shape, format shape.
Okay, I tried in Visio also, maybe in Visio, because all of the same package. I think it may be found also.
Yes, in Visio I did not try, but in HF in this PowerPoint you can easily do.
Has a package, yeah, I think. Yeah. It's okay, I got it. Thank you.
Yes, in this way you can design.
Yes. I want to just to know which option you use it. Shape effect, it's okay.
Yes. So in this way you can create many layers.
By try and error, yes. You need to try. Yeah. Thank you.
Okay, no worries. Now we can end the meeting. I hope today's session was very interesting session. Okay, and once we complete all these sessions, then we surely we will move fast towards the writing part. Okay.
Thank you. Many thanks.
Okay, so we can end the meeting. Okay, and see you tomorrow. Inshallah, or tomorrow we have a lecture of about what lecture we have tomorrow on dielectric resonator antenna. This is another interesting topic, more than implantable. I was doing a review of one paper on dielectric resonator antenna. I just gave them the reviews. This paper.
But the problem of this kind of antenna, actually, I don't try to work in it because the volume. Everybody now go to how to small size, how to make a compact. But it is difficult.
For dielectric resonator.
Yes. How we can do it is difficult, I think.
Yes, you cannot take small size, because if you take the small size, then it is more hard for you to fabricate dielectric resonator.
Actually, 3 years ago I tried to work on it, but I gave up.
But in my university, it is a good fabrication measurement facility of this dielectric
also a 3D printer to
yes,
to print.
we have many 3D printers in my university, in my lab. So I also like, if you someone like work on it, and surely this is a very new field. Okay, I am working on dielectric resonator antenna. I submitted my few papers in transaction and other, and inshallah I hope I will get good response. Okay, I have very good designs on circularly polarized, because it is easy to make circularly polarized dielectric resonator antenna. Okay.
What about the volume?
Volume is a simple patch antenna. It can be less than 30 cross 30 millimeter scale of the substrate. Okay.
What's the benefit of the dielectric antenna? Yeah, what's the advantage? And the other, by comparing with the other type of antennas.
We can discuss tomorrow if you want, because tomorrow we have a lecture on it and we can briefly explain each and everything about it.
Okay, thank you very
Okay.
much.
Okay, thank you, brother. Thank you.
Okay, thanks a lot.